Hello everyone, my name is Ali and today we'll be talking about forward and reverse mutations, and later we're going to be talking about reversible and irreversible mutations. Now, if you enjoyed this video or any of the videos that are present on this channel, feel free to subscribe and like down below. Let's start with rate of mutations. Now, they are very low, that if new mutations enter into a population, the fate of these mutations are actually not going to be determined by this parameter itself. It is going to be affected by non-mutational forces even more. If we assume that mutations are the only operating force, or only operating evolutionary force, however, I mean, if you want to remove genetic drift, if you want to remove natural selection, etc., this is going to be what we have. We've got the conversion of the capital A into small a, which is dominant allele, into a recessive one. It is going to be called forward mutations, and the rate of these forward mutations is going to be represented from now on as U. Now, the rate of the reverse mutations, which is simply the conversion of the small a, the recessive A, into the dominant A, we're going to be referring to that as V. Now, it is worth noting here that the reverse mutations are simply less common than forward mutations, and we're going to be taking an example of this later in the video. Now, if we assume a population in Hardy-Weinberg equilibrium, by the way, whenever we will talk about population genetics, it is extremely important to make sure that we assume Hardy-Weinberg equilibrium, or else this calculation is going to be simply extremely difficult. Now, and the only and the only evolutionary force acting as a mutation, the following can be inferred. In each generation, a proportion of the A are going to be converted into small a, and these are going to be referred to as forward mutations, like we mentioned before, and the number of mutations depend on the forward mutation rate and the population. What do we mean by this? And let's take an example in order to actually understand what we are talking about. In this example, we've got a population of 100,000 individuals. We've got a frequency of our allele at 0.1, and the mutation rate, the forward mutation rate U, is 10 to the power minus 4. By the way, we're going to get to the unit later on. If the population is 100,000 and P is equal to 1, by the way, just make sure that in the question we put the value at 0.1, and now we're taking it at 1.0, but we are going to be getting to the primary question later. So if the population is 100,000 individuals and P is going to be 1.0, the number of the forward mutations, like we mentioned in the previous slide, it is going to be 100%, which is the N, or the population, multiplied by the forward mutation rate, which is 10 to the power minus 4. Therefore, we're going to be getting the value of 10. Now, if the population, moving back to our question, if the population is 100,000 individuals and P, which is the frequency of our allele at hand, is 0.1, the number of the forward mutations is going to be simply the 10,000, because 0.1 multiplied by 100,000 is 10,000. Therefore, we've got 10,000 multiplied by the 10 to the power minus 4, which is going to be 1. Now, the increase in the P, or the increase in the frequency of our allele due to A, is going to be VP, which is the reverse mutation, simply. Okay, let's take this as an example. We've got A that is going to be changed to small a in case of forward mutations. And also, we've got small a that is going to be converted to large a in the case of reverse mutations. So if we want to calculate the increase, all we have to do is take the reverse mutations multiplied by the population, and this is how we get the increase in the frequency of our allele. If we want to, however, calculate the decrease in the frequency of our allele, all we have to do is calculate the forward mutation rate, since we're converting capital A into small a, multiplied by the population at hand. Now, the amount, if we want to reach a conclusion, the amount of the A, the capital A, decreased is as follows. The increase in A, which is the reverse mutations, minus the decrease in A. Simply speaking, we've got the amount of reverse mutations minus the number of the forward mutations. Eventually, though, the frequencies of the forward and the reverse mutations are going to be stabilizing, which means that the population has achieved equilibrium. By the way, just a side note here that this is going to be taking ages and ages and ages in order to reach this equilibrium, but this is going to be spoken about in a later video. This frequency at equilibrium for A is referred to as Q hat or P hat, whatever you're trying to calculate. So in this case, we've got Q hat is equal to the mutation rate, the forward mutation rate, U, divided by U plus V, which is the forward mutation rate, plus the reverse mutation rate. Next, if we want to calculate the P, the frequency at equilibrium of P hat, of our allele P, all we have to do is just calculate use a formula present on screen, which is the V, which is the reverse mutation rate divided by the forward plus reverse mutation rate. Now the frequency at equilibrium is no longer affected by the initial allelic frequencies, which is the reason we're not actually taking the population into consideration anymore. Now, if you want to remember that in the previous one or two slides ago, we mentioned that in order to calculate the mutations, all we have to do is multiply the mutation rate multiplied by the population. However, when you reach equilibrium, this is no longer needed, and all you have to do is use the formula at hand, and the population is no longer significant. In this example now, we're going to be looking at a frequency of a certain allele. We're going to be referring it to as P as 0.9 and the frequency of Q at 0.1. The forward mutation rate is going to be 5 multiplied by 10 to the power minus 5, and the reverse mutation rate is going to be 2 multiplied by 10 to the power minus 5. So we've got, the question is as follows: calculate the change in the allelic frequencies in the first generation. Now the change, obviously this is referred to as delta. So delta P is equal to, as follows: we've got the reverse mutation multiplied by the population. Since we're calculating the change, we have discussed this in a previous slide. So we've got the reverse mutation times the population minus the forward mutations times the population. And now we simply plug in our values, which is 2 multiplied by 10 to the power minus 5, multiplied by the 0.1, which is the frequency of the Q allele, minus the frequency of the Q allele. Then we've got minus 5 multiplied by 10 to the power minus 5, which is the frequency. Sorry, this is the forward mutation rate multiplied by 0.9, which is the frequency of the P allele. Now, the essence, the conclusion that we want to draw from here is that the answer is minus 0.000043, which is extremely small, and so this indicates that the mutation rate is very, very slow. Worth noting that in reference to the previous examples, mutations on their own are very slow, and this is what we mentioned before, and it could take thousands of generations to alter a species, and this also tells us that it is nearly impossible to achieve equilibrium when mutation is the only force acting. Now this is very important to note, because if mutation was the only force acting, it would simply be impossible. Now, let's talk about irreversible mutations and reversible mutations. First of all, in case of irreversible mutations, what we observe is that only A, capital A, it is going to be converted into small a. So this immediately tells us, even without looking at any graphs, we can immediately know that eventually all the capital A's are going to be converted into small a's, and we're going to be having a loss of the allele, that's capital A, and a fixation of the allele, small a. Now, continuing, this is only forward mutations are going to be occurring, which makes the decrease in the allelic frequency notably faster than if it were reversible mutations. We are going to be talking about in a few moments. Now, another thing to note here is that the lower allelic frequency in a population, the longer the time required to mutate. Now, this is apparent from the graph or the image that we are seeing here. It is because if the time required to decrease the frequency of a certain allele was stable, then it would have been linear. However, it is not, and this is what is showing in our image. Moving on to reversible mutations. In case of reversible mutations, we are going to be seeing both forward and reverse mutations. And this tells us immediately that since we always have capital A's converting into small a's, and we also always have small a's converting into capital A's, therefore, we are neither going to be having nor fixation of allele X or Y, or loss of allele X or Y. So this is going to be extremely important. So moving on, there will be no fixation of the recessive allele, because in the previous example in irreversible mutations, we simply at the end will get a fixation of the recessive allele. In this case, it is impossible, because there will always be reverse mutations, recalling that reverse mutations means small a into capital A. After tens of thousands of generations, they will reach some sort of equilibrium that we can calculate using the formula that we mentioned earlier.